Thank you, guys. Let's talk about bosons. With all of these particles, they interact in all sorts of complex ways. And we've basically boiled it down to 4 fundamental forces. Don't copy this down just yet. Oh, you can't see it. 4 fundamental forces. Don't copy this down just yet. Leave it there. Those are the electromagnetic force, which you're very familiar with after doing that topic much earlier. The strong nuclear force, which might sound a little bit familiar from when we did our nuclear unit back in year 11. We probably talked a little bit about the strong nuclear force. And that's the glue that holds these atoms together. The reason that protons can sit next to protons is because of their sort of way that they stick together with each other and also neutrons. So neutrons fill a dense nucleus. If you talk about uranium, for example, tons of protons in it, but also tons of neutrons in it. And the neutrons don't attract the protons to them with charge, their neutral charge. They just allow for the strong nuclear force to keep things attracted. Now, we're going to look at in more detail, but one of the weird things about the strong nuclear force is it can change to be repulsive depending on distance. So if these atoms come too close, if you take 2 neutrons and try and force them to touch, the strong nuclear force actually, we say that it will repel. And this is the way that these things can never superimpose. So we talked about superimposition of waves. Energy can superimpose. It can exist in the same space. You can have 2 crests exist in the same space and their effects get magnified. You cannot have 2 things with mass exist in the same place. And that's because energy does not interact with the strong nuclear force. It doesn't have this force. It only has the electromagnetic force, if it's electromagnetic radiation, which it generally is. So the strong nuclear force will actually repel things when they try and get too close, and we've observed that before. And it has a sweet spot too. This is the other weird thing about the strong nuclear force. It's really strong at a fixed distance, and then it gets weaker the further away you get. And if you get too close, it gets weaker until it becomes repulsive. So it's got this little crest in how strong it is, and I'll show you. I've got the diagram here actually. There's this little sweet spot where generally neutrons want to be that far away from each other because that's where the force is the strongest. And that force obviously will want to pull them closer, but then if they do get closer, it becomes repulsive and then they get further away. And so they find this sweet spot where they will sit next to each other. They attract protons. Protons are repelled by the electromagnetic force, but there's a point where the electrostatic force, however you want to think about it, there's a point where the electrostatic force is too strong and will make sure they repel. And there's a point where the nuclear force takes over and is strong enough to hold them together. So you have to get them kind of close first, protons. And then once they're close enough, the nuclear force kicks in and goes zoop and holds onto them really tightly, right? So it's this interesting interaction between these forces. So those are your 2 key forces, electromagnetic and strong nuclear force. Those are the main ones. There is also weak nuclear force, which is a really weird force, and it doesn't act in a way that you imagine forces to act. It's a bit of an odd thing. It's what's responsible for the situation we've spoken about before, beta decay, where a neutron can turn into a proton or a proton can turn into a neutron. So it's this almost internal structural force that will spit things out and suck things in to change the composition of protons and neutrons. So it interacts with quarks, and it can sort of swap quarks and make matter appear and all sorts of weird things. We don't go too into detail with the weak nuclear force, so we don't have to stress too much about all of that finicky stuff. And then the 4th one is gravity, and you'll see there's a little exclamation mark on gravity. That's because it doesn't fit the standard model. It doesn't work. It doesn't make sense. We don't have a model for how gravity works in the standard model. It doesn't seem to work. So gravity is the big breakdown here. In Einstein's general relativity, is the thing that we want to somehow merge with the standard model to make a grand unified theory, some sort of theory of the universe that actually works for everything. Because we don't have it right now. We don't have a complete model. We don't have the math to predict a lot of situations. So that's sort of the forefront of physics at the moment. Now, that brings us to what are those? The blue things. Anyone know? It says on this sheet. They're all bosons? What type of bosons? Guys, join us. What type of bosons are those? They're a type of boson. It says it on your sheet. The gauge bosons, right. And what's that big thing in the middle there? The Higgs boson. What's that? The scalar boson. So those of you who hadn't filled out that yellow corner yet, and Nicola, I think you need to fix this. Not a neutron. It is the Higgs boson. Now, the Higgs boson is newly discovered, and again, we don't know a lot about it, and it's not in your syllabus, so you should be aware that it exists. You don't need to know much about it beyond that. It is the only boson, and we're going to talk about what a boson is more generally in a second. It is the only boson that is called a scalar boson. The other bosons are called gauge or vector bosons. Now, what that means is they interact in 2 dimensions, or in space and time, in a sense, or in 3 dimensions of space, okay? So they're represented by vectors. They have a direction. They have a magnitude and a direction, okay? So for example, the photon, which is a particle that is responsible for the electromagnetic force, we're going to talk about that more in a second, but photons are what causes the electromagnetic force to work, and they're a particle that act in a direction. The Higgs boson just has some sort of scalar quantity. It doesn't have a direction, okay? So it's a particle that exists without any direction. It just has some sort of quantity. Really weird concepts, and you don't need to know too much about that, but you should be aware that there's 2 different types of bosons, scalar and gauge bosons, and gauge bosons are a vector quantity, okay? So your first gauge boson here is the gluon. We're going to do a bit of a summary table of all of this information in a second. That's why I've got the butcher paper here. I'm going to send you to your tables, give you a bunch of resources, and I'm going to ask you to put it into a nice, neat summary table as a group, which I think you can then consolidate into your notes quite effectively. But for now, we're just going to go over things generally so we have a bit of a sense for this. The gluon, you can see it has no mass, no charge. It is a boson. So it's a particle that carries the forces for us. Basically, if you imagine a field of space where the strong nuclear force can act, and the gluon is moving through that field and manipulating that field. And so if you want 2 protons, for example, to stick together, they continuously swap gluons. It's this weird sort of glue that swaps back and forth between them. They just transfer gluons back and forth, and it's that sort of connection that keeps them close together. It's this interaction. It's essentially a way of the universe sending information to each other going, you need to stay here, you need to stay here, you need to stay here, something like that. It's this really bizarre way that forces on a quantum scale actually function. They function by sending information in packets of bosons. So the gluon will bounce back and forth between particles that interact with the gluon and with the strong nuclear force, because not everything is affected by it. And they say, stay here, or come closer, or go further away. And just by their existence, that is how the universe will know what its rules are, I guess. Okay, really sort of weird stuff. The next one worth talking about is the photon. So photon you're very familiar with. It is in fact not much different to the gluon. It is chargeless. It does have a spin, unlike the gluon. The gluon has it doesn't have mass. Sorry, it does have spin. They both have spin. The photon, you can see it has a mass there, but again, that's a mass as a type of energy. Okay, we do say the photon is a massless particle, but it doesn't have charge and it does have spin. The photon is the mediating particle for the electromagnetic force. So we've spoken about how when electrons are spinning or changing direction, they constantly are shooting out electromagnetic radiation in the form of photons. If you want to push a electrically charged particle, you actually need to bring something electrically charged close to it. And what it does is it shoots a photon across that gap and says, go away or come closer, depending on what the charges are. So again, it's this great communicator between things that exist in an electromagnetic field. And again, not every particle interacts with the electromagnetic field. Can anyone guess from our standard model that we have what particles don't interact with photons at all? Quarks. Quarks have charges, so quarks will interact. Leptons, specifically what? Neutrinos. So neutrinos having zero charge, they're just a quantity of mass. They don't interact with photons. Every other particle there does. Even when we talk about, a neutron, which is in itself a net neutral thing, it has up and down quarks. It has hotspots of charge within it. And so if a photon comes near a neutron, there is still an interaction. It won't necessarily develop in any sort of observable effect unless you broke that neutron down into its quarks and separated them. But a photon can still interact with even a neutron with a charge of zero. It just doesn't necessarily result in any net change. But neutrinos do not at all. You could pass light straight through neutrinos, nothing would happen. Every other particle, you would observe something. Okay, last two are the W and Z bosons. I'll remind you the Higgs boson we're not super interested in. We're not going to worry too much about. It's quite complicated. It's a bit weird, and we still don't know the full story behind it. It's still under research. So the W and Z bosons are the last things, and they are what allow us to swap charges in quarks and actually allow this nuclear change where, in particular, beta decay, beta positive or beta minus decay, which results in a neutron turning into a proton or a proton turning into a neutron through the absorption of an electron. There's some boson which communicates that interaction, and it happens to be the W and Z bosons. W bosons come in two flavors. They can be positive and negative. Flavors, whatever, types, I don't know. Positive and negative W bosons. And then the Z bosons have no charge, okay? So they, again, are just an interaction on the sort of mass level, not on a charge level. You can see they're quite heavy too, which is somewhat interesting, how much sort of mass they carry or energy they carry. Cool. So, matter in quarks and leptons, bosons, which are the force carriers in the photon gluon and the bosons, the W and Z bosons, again, W having a positive and a negative version, and then the scalar boson, which we don't know much about and don't really understand, the Higgs boson. What I want us to do is make a table like this, okay? So just to be clear, this is what this table is. Looks something like this. And I'm happy for the weak nuclear force to still get all of this information. But the gravitational force, we're just going to fill up with question marks, except for strength. We are going to compare the strength, okay? So everywhere I put an X here, you guys are actually going to fill out. You're just not going to know for gravity what the mediating particle is. There is a proposed particle that allows gravity to exist. It's the graviton. We haven't discovered it. We don't know if it's real. But if we find a graviton, then we have a way of describing how gravity works as a force on the standard model. Right now, we don't know if it exists, and we can't find it. So, don't know. So you guys are going to fill out the information here, here, and here, and here, and here, and here. And you're going to do a big rough copy on some butcher paper over at your lab counters in big groups, okay? So I'm going to hand out these big sheets of paper. You're going to get big pens, pencils, and you guys are going to jot down a bit of a table like this. And here is the key information I'm going to give you. That's everything I'm going to give you. So what I'm asking you to do is take these 2 tables from your textbook and 1 image which I grabbed off the internet and used them to try and describe these forces, identify their strength, and I mean, you're literally, for the strength, you're just reading off that bottom table, basically. Keep it simple, stupids. Yeah. Mediating particle, again, that's pretty well given in the tables here. And the particles which it interacts with, or the particles experiencing the force, okay? I'm also going to hand you these. These are my little matter, antimatter, force interaction tables, okay? You can see the red, blue, green boxes. Those are the forces, and they surround the particles that they interact with. You can also see scattered throughout those boxes the bosons, the W bosons, the photons, the gluons, all of those bosons. They are within the boxes where they interact with the particles, okay? Hopefully that's clear. All right, any questions about that? What the plan is? I'm going to have to swap in between this and the other stuff. I'm going to leave this up to start with, and I'd love you to fill this big page first with a template for that. Not going to need a lot of space, not going to need a lot of space, not going to need a lot of space. We'll need a fair bit of space. Enough for probably a bit of a paragraph or a couple of sentences, and maybe even a picture or a graph. Okay? Off you go into groups. Go to the lab counters. Probably easier for you to work in groups at them. I'll bring around your butcher paper.